Hello guys, welcome back to Where Math Circles Math Counts training. This is session 10 of a 12-part series, so if you haven't watched the other videos, go ahead and watch those. And once you're done with that, come back to this one. My name is Mugil Shanmugam, and I'm going to be presenting all these videos for you guys. Okay, so let's get right into it. So what exactly are we going to be learning today? Session 10. So today we're going to be covering the following broad problem types: proportion and slow fast watch problems, work, word problems, and nets. And we do have some subtopics underneath these broad problem types. We're going to be learning some definitions, some basic knowledge, and just imagery or like how you can visualize a net. And we're also going to be learning some more important formulas. Okay, so let's get right into it. So basic knowledge for proportions. So the first thing you need to know about proportions is you need to know what ratios are. Ratios are used to compare two numbers. An example is A is to B, right? So you're comparing A and B here. And they do have some divisor in between them. If you multiply A by something, you're going to get B. So that's basically a ratio. A proportion is an equation of two ratios. So A is to B, you can also write it as A over B. So here I have A over B, and this is equal to C over D. So this is one ratio, and this is another ratio, and they're equal to each other. So when two ratios are equivalent to each other, or they're equal to each other, then this is a proportion. So the above proportion is equivalent to AD is equal to BC. How do we get that? Well, we multiply the numerator times the denominator, so A and D, so we get AD on our left-hand side, and B times C will give us BC on our right-hand side. So that's how we get AD is equal to BC. Now, we can have some variations on the original proportion, so we have AD is equal to BC. Now we can also change this to A over C is equal to B over D, D over B is equal to C over A, B over A is equal to D over C. So once you're given these initial values, you can change it in these ways to get different proportions that may meet your needs better on a problem. Now we can also make a few more variations. So here we have A plus or minus C over B is equal to C plus or minus D over D. Another one is A plus or minus B over A is equal to C plus or minus D over C. And A plus or minus C over C is equal to B plus or minus D over D. And so basically what we're doing here is we're given our original proportion, A over B is equal to C over D, and then we're going to add something or subtract something, and the proportion will still stay true. Here's some more. A plus C over B plus D is equal to A minus C over B minus D. Another one is A minus B over A plus D is equal to C minus D over C plus D. So basically, we're taking this original proportion and we're modifying it in different ways to create new proportions that are still true. Now, if A1 over B1 is equal to A2 over B2, which is equal to A3 over B3, and so on until AN over BN, then you can rewrite this as A1 plus A2 plus A3 all the way to AN over B1 plus B2 plus B3 all the way to BN is equal to A1 over B1. So here, again, this ratio is being compared to this ratio, and they're equal to each other. Okay, so let's go over slow, fast watch problems. And here's some steps. In general, for these problems, first find the difference between the slow and fast watch that occurs in an hour. So then you have to set up a proportion. It should generally look something like this. So first, what I'm going to do is after an hour, I'm going to find where my slow watch is at and where my fast watch is at. So after an hour, maybe my slow watch has passed 58 minutes, and my fast watch has passed 100 or maybe 62 minutes, right? So then I can find the minute difference between the two, put that over 1 hour, and then we can find the minute difference desired over X hours. So let's just say that in 1 hour, I get a 4-minute difference, and I want a 60-minute difference. So then I can solve for X here and find how many hours it takes to get that difference. So as it says here, solve for X, then add X hours to your start time to find the time at which the desired time difference will be observed between the watches. So this one is not that hard. All you're really doing is you're going to solve for X here to find how long it takes to get the minute difference you desire. And this will be given in your question. All you're going to be solving for is X. Then one thing you want to make sure to do is make sure to add X to your start time, because usually they'll ask at what time will they be the same, or like at what time will this difference be seen. They're not going to be asking how long it will take. So make sure to add X hours to start time to get the time at which your minute difference desired will be observed. Okay, so here's a sample problem for this. So 2 clocks are set at 6 a.m. One clock gains 30 seconds each hour, and the second clock loses 1 minute every hour. At what time will the faster clock be 30 minutes ahead of the second clock? And this is from the Continental Mathematics League. Okay, so again, you just want to go back here and follow the steps. You want to set up this proportion. Once you've figured everything out, solve for x and add x to your start time if you want to get the answer correctly for this one. Okay, so go ahead, pause the video, and solve this problem. Okay, hopefully you paused the video and hopefully you got your answer. Let's go over how we can get the answer for this one. So the first step is to find the difference between the 2 clocks after 1 hour. So after 1 hour, the first clock will be at 7 and 30 seconds a.m., right? How do we know? Because it says 1 clock gains 30 seconds every hour. So after an hour, it's gained 30 seconds. The second clock will be at 6:59 a.m., right? How do we know this? Well, it says that it loses a minute each hour. So it's going to be at 6:59 a.m. This means that there's a difference of 1 minute and 30 seconds between the 2 clocks, right? Because there's 30 seconds here and 1 minute difference here. So when you add them up, you get 1 minute and 30 seconds. So 1.5 minutes is the difference we see in 1 hour, and we want a 30-minute difference. So how many hours will that take? Then we can just do our cross multiplication. So 1.5x is going to be equal to 30. And then when we solve for x, we're going to get x is equal to 20 hours. So the clocks will have a difference of 30 minutes after 20 hours. Now this is at 6 a.m. plus 20 hours, which is 2 a.m. So that one was not too hard. All you really had to do was set up your proportion correctly, and then the answer would be easy to find. All right, let's move on to our next topic, work word problems. So the first thing we're going to be really learning is rates and kind of time, and then we're going to branch this into what if 2 people work on a job, what if 3 people work on a job, and so on. So if 1 person or a machine can complete a job in t unit of time, then the rate of work is r is equal to 1 over t, or r times t is equal to 1, with t equal to total time. So your rate is going to be 1 over the total time it takes to complete this job, or your rate times your time is going to give you 1. Now, sometimes you won't finish the job completely, right? So if the person or the machine spends a t unit of time doing a job, then the w portion of the work job done is t times r, which is equal to t times 1 over little t, which is equal to w. So let's break this down. So t is how much time you've already spent on it. And your rate is basically 1 over t. We learned that over here, right? So this is the same as big T times 1 over little t. Now, t is the total time it takes me to complete this job. So I've spent some of the time here, but I have not completed the job. And t little t basically is going to be how long it's going to take me to complete the entire job. Now, when I multiply how much time I spent times my rate, then I get how much of the job I've completed. So we'll learn how to apply this when multiple people are working at different rates. Now, if n people work together to complete the job in t unit of time, the rate for each person is r is equal to 1 over n times t. So for 1 person, it's r is equal to 1 over t, right? So 1 over the total time it takes. Here, we're going to multiply the total time it takes. We're going to multiply that by the number of people working and 1 over that. That's how we get our rate here. Now, this is going to be expanding on this one. So if n people spend a t unit of time working on a job, and the portion of the job done is w, then t times r. So this is what we saw here too, but this was for 1 person. Now we have multiple people. So it's going to be t times 1 over n times t. Why? Because our rate is now equal to 1 over nt. So that's how we got t times 1 over nt. And that's going to be giving me my w, or how much of the job has already been done by these people. So basically, this is for 1 person and this is for 1 person. Then we're expanding it to get what if n people work on the job. So what if any number of people work on the job? Now you may be asking, well, what if they work at different rates? Surely they're not all going to have the same rate of work. So that's what we're going to be learning on the next slide. So here we have some more words on rate. So if 3 people of the same rate work together for t hours, and the amount of the job done is w, then t times r is equal to t times 1 over t plus 1 over t plus 1 over t, which is equal to t times 3 over little t, which is equal to w. So basically, this is for 3 people. That's why we have 3 of these, right? And they all have the same rate. So the rate is just going to be 1 over t for each of them. And when we do that, this is basically 3 over little t, right? And then we can multiply to find how much of the job has been done. W here is the amount of the job done. Now, sometimes I'll have different rates. So here I have 3 different rates for 3 different people, right? The first guy works at this rate, second guy works at this rate, third guy works at this rate. So what I'm going to get is t times 1 over t1. So that's my first total time taken, second total time taken, and third total time taken. And when I multiply that by big T, or how much work they've put into the project, not how much work, sorry, how much time they've already put into the project, then I get how much of the project has already been done. Now, we can also simplify this for 2 people. Here we're doing it for 3 people. If you want to do it for 2, just take out your R3, take out your 1 over T3, and that's how you're going to get how much it takes for 2 people and how much of the job they've already done. Okay, so that may have been a lot to take in, but just remember that basically so we already learned how the rates work. Now we're just going to expand it if different people are working at different rates. That's why we have R1, R2, R3, because each one is working at their own rate. Each one, if he's working alone, would take a different total time to complete the job. And that's how we're going to solve these. Okay, so if n1 people at the same rate and n2 people at the same rate work on a job together for t unit of time, and the amount of work done is w, then t times r1 plus r2 is equal to t times 1 over t1 into n1 plus 1 over t2 into n2, which is equal to w. Okay, so before we just had 2 people. Now we have 2 groups of people. They're working at different rates. So that's why I'm multiplying by n1 and n2. That's the only change here. I'm multiplying by n1 and n2 because now I have a group of people. And remember, if we go back, we learned that the formula for a group is 1 over n times t. So that's why we're expanding it over here to t1 into n1. Now, for one entire job, if n1 people at the same rate r1 can complete the job in a t1 unit of time, and n2 people of the same rate r2 can complete the job in a t2 unit of time, then 1 over r1 into n1 into t1 is equal to 1 over r2 into n2 into t2. This is just a proportion. And if it's just 2 people, then it'd be 1 over n1 into t1 is equal to 1 over n2 into t2, and this is with the same rate r. Okay, so basically here we're just learning what if there's groups of people working on the same job. All right. So here's our last few work formulas. So for one entire job, if n1 people of the same rate r1 can complete w1 amount of the work in a t1 unit of time, and n2 people of the same rate r2 can complete w2 amount of the job in the t2 unit of time, then w1 over r1 into n1 into t1 is equal to w2 into r2 to n2 into t2. This is over r2 into n2 into t2. So this is an expansion of the earlier proportion. We're just adding a w1 over, because this is if they can complete the job, and this is when they cannot complete the job, how much of the work they've already done. Now, sometimes the job is not constant, like linear change with the rate of x per unit time. For example, maybe you're cleaning a pond, but it has a constant rate of growth. Or cows are eating grass, but the grass is always growing back up. So then you're going to do w1 plus t1 times x over r1 into n1 into t1, which is equal to w2 plus t2 into x over r2 into n2 into t2. So again, we're expanding this one now. We're just adding this linear equation part of it. So because this is like constant growth, right? We're always getting new growth to combat what we've already done. So basically, you're just learning how we can expand this for more people. And then here we're setting up proportion if different groups of people can do it at different times. How are they equivalent? And then we've expanded that to if they don't complete the job, but they only do a part of it. And here, if there's linear growth, combating the work they've already done. Okay, so that was a lot of formulas, I do admit it. However, what you can do to remember these is if you remember the basic formulas back here, then you can expand these when you need them for bigger groups of people. And based on that, it's pretty easy to solve these problems if you remember the basic formulas. So don't spend your time memorizing all of them. Just remember the basic ones, and eventually, over time, the harder ones and the bigger ones will just become second nature. Okay, so let's go over our sample problem for this one. Jerry worked for 1 day on a project that he could have completed alone in 9 days. So we know that his little t is 9. Bill joined Jerry the next day, and they worked together for exactly 3 days to complete the project. How much of the job did Bill do in those 3 days? Express your answer as a common fraction. Now this is from the 2008 MathCounts handbook. Okay, so we know his little t is 9. It'll take him 9 days to do it by himself. Now you have 2 people, and they may be working at different rates. They probably are. So based on that, you can solve out this problem. Use your basic formulas. Right, pause the video and try to solve the problem. Okay, hopefully you solved the problem. Let's go over the solution. So the work W done by Jerry in 1 day is W is equal to T times R. Remember, this was our basic formula, which is T times 1 over T. Here, he's worked for 1 day, so 1 times 1 over 9, because it takes him 9 days to complete it by himself. If he was doing it only by himself, it would take him 9 days. So 1 times 1 over 9, which is just 1 over 9. So Jerry has already done 1/9 of the project. So now there's only 8/9 of the job left. 1 minus 1/9 is 8/9, right? So now we have 2 different people working at 2 different rates. So how do we solve this? Well, W is equal to T times R1 plus R2, which is equal to T times 1 over T1 N1 plus 1 over T2 N2. So here you can discount this N, right? There's just basically 1 because there's 1 person in each group, 1 person in each rate group, because you have Bill and Jerry. So basically 1 where it says N1 and 1 where it says N2. So now we can just basically plug in our values and we can solve for this one. 3 times 1 over 9, okay, because 1 over 9 is Jerry's rate. We already figured that out, remember. 1 over T1, so 1 over 9 plus 1 over T2. We don't know how long it would take Bill to do this all by himself. And this is equal to 8/9, because this is how much of the job is left, and this is how much of the job they have to do. So we can solve this linear equation for T2, and we get that T2 is 27 over 5. So now, if we want to find out how much of it Bill did in particular, we can solve by using our formula. So Bill worked on it for 3 days. So that's why we got our 3 here. Well, okay, there. So he used 3 days. He worked on it for 3 days. And we're going to multiply that by 1 over T2. Remember, that's our formula, T times R. So our R is 1 over T2, and 1 over T2 here is just going to be the reciprocal of 27 over 5. So that's going to be 5 over 27. So that's going to be 3 times 5 over 27, which is 15 over 27, which is 5 over 9. So Bill did 5/9 of the job. Jerry did 1/9 of the job before Bill joined, and then Bill did 5/9 of the job once he joined. So here we use 2 different formulas, and then we solved for our T2, and then we just plug that back into our formula to find how much of the work W done by Bill. Okay, so let's move on to our last topic. So nets of a cube. So basically a net of a cube or any shape basically is when you fold up these boxes here, you're going to get a cube, and that's called a net. A net is when you basically laid out all your squares on like a fat piece of paper, and when you fold it all up, that's when you get your actual cube. So a cube has 11 nets, as you can see in this picture. Now, given the net of a cube, and asked to find the vertices that meet with a given vertex when the net is folded, right? First, draw a line across 2 square faces from the given vertex to a point A. So we can just take any net here and try this, right? Let's just say I take this net. So if I'm given this vertex, I'm going to draw a line across 2 square faces. So across this face and across this face to this point. Now find 2 other points that are the same distance away from A, a line across 2 square faces. So this point is also the same distance away because 1, 2. And based on that, not from this point, it's 1, 2, right? 1, 2. And basically you just find different squares that are 2 square faces away from your communal point. Now you'll find 3 points, and these 3 points will meet when the net is folded. In a cube, 3 faces will share a vertex. So basically you're going to be given a net, you find a point, any point, usually they'll give you this point. Then what you're going to do is you're going to draw a line from this point to another point, and you label this A. Now you find 2 other points that are equidistant from A. So the same distance from A, they have to be the same distance from A, and these 3 points that you just found, they will all meet at when they're folded. When the cube is folded up, these 3 points will meet. And we do have a sim problem on this, and I've drawn it out there so you can see it there if you want better help visualizing this. Okay, so net of an octahedron. So given the net, first let's go over what an octahedron is. An octahedron is a solid with 6 polyhedron vertices, 12 polyhedron edges, and 8 equivalent equilateral triangular faces. So basically it's a 3D solid, right? And you can see different nets here. So given the net of an octahedron and asked to find the vertices that meet with a given vertex when the net is folded, we're going to be doing the same thing. Except here we have triangle faces, we don't have square faces. So I'm going to be drawing my line across 2 triangle faces. So first draw a line across 2 triangle faces from the given vertex to the point A. Then find 2 other points that are equidistant from this point A. And then the 3 points will meet when the net is folded. In an octahedron, 4 faces will actually share a vertex. So basically, for both the net of an octahedron and over a cube, we're basically going to find one point, we'll be given a vertex. From that vertex, we're going to find a point that is 2 square faces away, then find 2 other points that are also equidistant from that, and you know that those vertexes, or the ones you just found, the vertices that you just found, will all meet together. Okay, so let's move on to the net of a tetrahedron and a dodecahedron. So a tetrahedron has 2 distinct nets. The regular tetrahedron has 4 vertices, 6 edges, and 4 equivalent equilateral triangular faces. And here are your 2 nets of this. So your surface area for this is going to be rad 3 a squared, and here your volume is 1 over 12 rad 2 a squared. Okay, so basically 2 simple formulas that you can use when you're given your tetrahedron, right? And you'll be given these values on the MathCounts exam most likely. Now, a regular dodecahedron has 20 vertices, 30 edges, and 12 pentagonal faces. It has 43,380 distinct nets. 3 faces share 1 vertex. So obviously, I can't show all 43k of these nets down here, but I have given one picture of this, basically a net folding to make the shape. So if you see, this is the original net of the dodecahedron, and it slowly folds into your 3D shape. And that's basically what a net is. Okay, so here's some important formulas you're going to be using when you know nets, or like when you're given a net. So Euler's formula is faces plus the number of vertices is going to give you the number of edges plus 2. Now the edges and faces formula says the number of edges is equal to the number of faces times the number of sides of the faces divided by 2. So if you have a cube, all the faces are squares, and squares have 4 sides. So that's how I got my 4 here if I was solving for a cube. So basically, these are 2 pretty simple formulas. You're just plugging in your number of faces, your number of vertices to find your number of edges plus 2. Now, the perimeter and vertices formula is perimeter is equal to 2 into the number of vertices minus 2. And P is the perimeter of the net of a regular polyhedron. Now, pentaminoes are something interesting. So they are flat shapes made by joining 5 identical squares together, touching the full edge. So these are different pentaminoes you can see down here. Basically, they're made of these 5 squares that touch each other, and when you fold them up, they create new shapes. Okay, so again, these were 3 important formulas, but they are pretty simple as long as you just plug in correctly. It's not a lot of math to do, it's just plugging in the numbers correctly once you give them. Okay. So here we have stars and regular polygons, star polygons and regular polygons. So star polygons are constructed by connecting evenly spaced dots on a circle with equal segments. Now, if the segments do not cross each other, the figure is a regular polygon, like a pentagon or hexagon, right? They don't have any segments crossing each other. Otherwise, if the segments do cross each other when you're connecting them, then it's a star polygon. So S of n is the number of different star polygons with endpoints that can be constructed with one continuous path. So when you're given endpoints, how many star polygons can you construct? And here's your formula. S of n is equal to Euler's totient function over 2. Now, how do we solve for Euler's totient function, which is basically this Greek symbol of n? It's called Euler's totient function. Now, we learned this a few sessions ago when we were learning about mods, but basically, here we have n. We're going to break n down into prime factorization. So the first prime to whatever power times the second prime to whatever power, and so on. Now, to find our totient function, what we're going to be doing is the first prime to the power whatever minus the first prime to the power minus 1. And so on until we get to our last prime to the last power. So if you solve it out, we went over this and we did practice on this when we were going over mods. If you use this function and then divide it by 2, you'll find how many star polygons you can construct with endpoints in the continuous path. Now the number of regular polygons with end dots. So the same problem, but this time you're going to be asking like how many regular polygons can I form? Then this is going to be d of n minus 2. And d of n is the number of divisors of n. So if you find how many factors n has here and subtract 2, you can find how many regular polygons you can form. So these are just two different functions you can use when asked to find the number of star polygons or regular polygons that you can form. Okay. Here's a sound problem. And here, that's basically what I was talking about with drawing out your lines across two square faces. The solution will show how you can visualize this. So when this net of 6 squares is cut out and folded to form a cube, what is the product of the numbers on the 4 faces adjacent to the one labeled with a 1? So this is your face labeled with 1. What are the 4 faces that will be adjacent to it? And what is the product of them? And this is from the 2003 MathCounts chapter sprint number 12. So go ahead, try to solve this problem. I recommend trying to draw this out and then drawing your lines. It'll be easier that way. And if you try doing that and multiply, you should be able to come to the answer, but I will go over the solution. So go ahead, pause the video, and try to solve this one. Okay, so hopefully you solved it. Let's go over the answer. So after selecting the vertex C, vertex C, so I've chosen this because it's on my first face, right? We find a point that is 2 faces away. So if I draw a line across 2 faces, I get this point right here. I labeled it with a dark square. Now we find that vertex A and vertex B are equidistant from this, right? Vertex A here and vertex B here. So they're on face 4 and 6. They're equidistant from this point, from this square that I shaded in. And they're the same distance away as C. So that's how I know that faces 4 and 6 will be adjacent to 1. They'll be touching each other. Now, we also know that face 2 will be adjacent to face 1 by virtue of its position, because face 2 is right here, and it's literally touching face 1 on a whole side. So that's how we know that face 2 will also be adjacent. So we know 3 of the 4 faces that will be touching, 2, 4, and 6. Now, taking vertex D of face 1, we find a point 2 faces away. Okay, so now we're taking another vertex of face 1, point D. So when I draw D and I draw a line across 2 square faces, I get to this square that I drew right here. I didn't label the point, but I just drew a square. Now, another face, which has a vertex which is equidistant, is E. If you can see, E has the same distance away as D to this non-filled in square. So that's how I know that face 3 will be the final face that is adjacent. So then we know that we have 4 faces that will be adjacent. 4, 6, 2, and 3. And when I multiply that, 4 times 6 times 2 times 3, I'll get 144. So that means that the product of these numbers will be 144 for this problem. So this is what I was talking about when I'm saying draw the lines across the faces. This was basically what I meant. But in the end, what you really need to do was, if you drew this out, it was pretty easy to solve, as it was much easier to see when you actually drew out the lines and you figured out which faces were adjacent. Okay guys, thank you so much for watching. Please like and subscribe if you enjoyed the video, and leave a comment with any questions. Thank you, and I'll see you in the next one. Bye.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email, but without the info and the end. So bye!